I'm just finishing the first year of my PhD, so I wanted to talk a little bit about my most recent project, which concerns data partitions and phylogenetic signal in my favorite group, the rodents. So, as we've already heard, one of the major drawbacks in paleontology is that when something dies, it decomposes. And this inevitably results in a loss of information. And I'm sorry, I couldn't resist including this rather humorous figure of a rather dramatic panda death and then fossilization. And unfortunately for us, decay is not a homogeneous process, and some body parts preserve more well than others do. For example, if you're studying mollusks, you might find a lot of fossilized shells, but not much else. And if you study mammals, you might find you have lots of fossil teeth, but maybe not so many postcranial characters. So one question we often ask ourselves is, does the preservational bias really matter? And does missing data have a negative effect on reconstructing phylogeny? And it would also be really useful to know if some characters would be more useful for phylogenetic analysis with regards to this. And these are really important questions because we rely on the accurate placement of fossils for calibrating rates of change over time, and they're our only really direct source of evidence for big macro evolutionary transitions. But luckily, lots of people, as you heard, have been working on this. So in 2013, our colleague Robert Sanson and Matthew Wills found that the bias towards hard tissue data preservation distorts evolutionary trees. So when soft tissue characters were excluded from analyses of living vertebrate taxa, this caused downward slippage, and these taxa occupied more basal positions on the tree, appearing more primitive, and this was quite worrying for anyone who was working on fossils. Then in 2015, a study by Partition found that hard tissue data is good for phylogenetic analysis, and they used a method called artificial extinction to take a living mammal from a well-corroborated tree and to reduce its characters to those preserved within a real mammal fossil, which they called a fossil template. And they found that these artificial fossils, based on the fossil templates, recovered very similar positions in the tree to their living counterparts. And furthermore, they found that the more data a fossil template had, represented here by little black squares, the better it performed. Furthermore, if you allocated character states to a template randomly, shown here in red, it performed much more poorly than the real fossil did. And finally, they found that the more partitions a template sampled, the better its performance again. So all in all, this suggested that fossils were quite good if you sampled across many different character partitions. And this particular result was supported in a study by Mans, Sansom, and Wills, who also advocated sampling characters widely across partitions. And of course, just recently, Robert Sansom and colleagues found that dental data in particular conveys a different phylogenetic signal to osteological characters, and that these dental partitions are significantly less congruent with molecular trees than osteological characters are. And so it seems we can all agree that it's best to sample characters from as many different partitions as possible, but there's still some disagreement over the phylogenetic signal contained within particular partitions, especially dental data. So my specific interest is the phylogenetic signal contained within rodent characters and how partitions optimize on rodent trees. And in particular, I'd quite like to know if the clades of different depths across the tree are supported by the same or different partitions. So for example, are more superficial clades near the tips of the tree supported by the same characters as those at the bottom of the tree nearer to the root? And rodents make quite a good case study for this because they comprise a huge chunk of mammalian diversity. They also have a great fossil record, and our understanding of rodent systematics has improved in leaps and bounds over recent years, so we have a pretty good idea of how they're all related to each other. So to help answer my questions, I've been looking at this data matrix of rodent and lagomorph species compiled by Asher et al. And my supervisor and I have been continuing to add data to this. We've so far got 42 fossil taxa, 29 extant taxa, and about 224 hard tissue characters. And so I made this tree here using the data matrix, and I constrained it using Favre et al. As a backbone. And this backbone is a well-corroborated tree based on molecular sequences for over 1,200 rodent species. And on it you can see the lagomorphs, which are rabbits and hares. And then we've got the three big rodent groups, the mouse-related clade, squirrel-related clade, and guinea pig-related clade. And unfortunately, my mouse-related clade isn't completely resolved, but I'll be referring to this as my well-corroborated tree for the rest of my talk. So, to see if clades of different depths are supported by different partitions, I firstly traced character histories across my well-corroborated tree, and I used the program Mesquite for this. And this basically reconstructs character states at ancestral nodes to give you an idea of where synapomorphies occurred. Then what I did was I measured the median distance between unambiguous character changes and the root of the tree. So in this example, curved decisors appeared in the rodents and rabbits here. And this clade is 1, 2, 3, 4, 5, 6, 7, 8 bifurcations from the root. So fairly simple. So to see if these distances of character changes vary across partitions, I had to allocate each of my characters to a partition. And there are several ways of doing this, and perhaps one of the most simple. You can have craniodental characters, and then you can have a partition of postcranial characters. But you can split this up a bit more. You can have a dental partition, a cranial partition, and a postcranial partition. This is quite popular. But you can basically have as many partitions as you want. And so here I've split the characters up into 11 partitions all across the skeleton. So time for a few results. Here on the y-axis, you can see the depth of my unambiguous character changes from the root of the tree. And on the x-axis, we've got our data partitions. So here it would appear that there is no significant difference between the cranial, dental, and postcranial partitions, and that these characters support clades of various depths across the rodent tree. But this changes slightly when we split our characters up into 3 partitions. Now there is a significant difference. And it would appear that the dental characters optimize as synapomorphies closer to the root of the tree than cranial characters do. And to me, this would suggest that the signal contained within dental characters maybe has a bigger impact on more basal clades than the cranial characters do. And this, to be honest, wasn't what I was expecting at all. And once we split our characters into 11 partitions, we get a lot more significant relationships. For example, the brain case characters, they support the most superficial clades on my rodent tree. And this is followed closely by rostrum characters. And again, dental characters seem to optimize as synapomorphies closer to the root of the tree, although there is quite a large range there. Middle ear characters, they also support clades a bit more closer to the root of the tree. And then my other partitions are mainly somewhere in the middle. And unfortunately, I don't really have enough data to look at the axial characters or pelvic girdle characters in much detail, simply because I just don't have enough characters for them to scrutinize them. But they clearly do somewhere down here near the bottom of the tree. So with that in mind, it does seem to be the case that different clades of various depths are supported by different partitions. So my next question was, if we exclude these partitions, would that then cause the taxa to move up or down the tree? And my thinking was that if you remove a partition which supports more superficial clades, surely this would cause the taxa to show stemward slippage and move down the tree. I also thought that if you removed a partition which supported more basal clades, then this would cause the taxa to climb up the tree, as in crownward slippage. So I repeated, for each partition, I repeated the analysis with those characters excluded and recorded whether they showed stemward slippage or crownward slippage. And here are my results. for each excluded partition, you can see in orange the percentage of taxa which showed stemward slippage, and in blue, the percentage of taxa which showed crownward slippage. And then in gray, we've got stationary taxa which don't move up or down. And there was quite a bit of variation. As I expected, removing the brain case partition, which supports the more superficial clades, causes almost all of the taxa to fall down the stem. Removing the rostral characters, which also optimize the superficial clades, also show stemward slippage, but not to the same extent. But interestingly, removing partitions which supported more basal clades didn't actually result in much crownward slippage. For example, removing the middle ear partition, this actually caused most taxa to move down the stem. So even though middle ear characters optimize closer to the root of the tree, they may contain some sort of hidden signal to support clades of more superficial depths. And the most extreme result was excluding the dental data, and this caused almost complete stemward slippage. And this is down to the number of unresolved taxa. So here we can see the percentage of partitions shared between my well-corroborated tree I showed you at the beginning and the trees resulting from excluding each partition. And as you'll notice, it doesn't really matter which partition you knock out, with the exception of dental data, of course. They all more or less recover around 50% of their partitions that I have in my optimal tree. When you exclude dental data, though, what I got was just one massive polytomy, and there are no shared partitions. But this could suggest that maybe there is useful signal in the dental partition for rodents. However, I think you have to bear in mind that dental characters are 40% of the stator matrix. But interestingly, if you exclude every single partition except dental data, you actually recover 25% of the partitions. So in this case, it's much more damaging to exclude your dental characters than it is to exclude all other partitions. And so even though dental data by itself is more noisy than when you combine it with these other partitions, by ignoring the dental characters completely, you lose out on a lot of useful signal. So to me, this all suggested that each one of these partitions is a valuable source of phylogenetic signal in rodents. And you could maybe argue that the teeth are particularly important for this particular group. And I think it also highlights what has been said before by Partition and all, and Sansom and colleagues, that you really have to sample your characters across as many partitions as possible, because excluding any one of these partitions had a negative effect on congruence with the optimal tree. So a few conclusions I've come to are that data partitions in rodents contain different phylogenetic signals. So we have some partitions supporting more superficial clades, such as the brain case and the rostrum. And then we have partitions which support more basal clades, such as the teeth. And of course, removing any one of these partitions, well, if you remove the partitions that support superficial clades, then the taxa move down the tree, as in stemward slippage. But this also happens when you exclude partitions which support more basal clades. So perhaps there is some hidden signal within these partitions to support clades of various depths. And of course, excluding any one of these partitions has a negative effect on congruence with your optimal tree, especially in the case of dental data. So just to highlight again the importance of sampling as many characters as possible from across as many partitions as possible. I'd like to thank the Claire Barnes Studentship for funding, to the organizers, and of course to you all for listening. So thank you very much.